Hey, thanks for inviting me to come speak. So I'm going to talk about the risk of deploying black box models in mission-critical domains like healthcare. So just to give you a warning, I don't have any formal training in machine learning in healthcare. I've been doing machine learning in healthcare, though, for the last 25 years or so. So I've been working with healthcare data for a long time. And I'm going to spread a little bit of doom in the beginning, but then don't worry, I'll show you there's light at the end of the tunnel as we go further into the presentation. So there's a number of people who I should thank here. Some of them are grad students, some are professors, some are colleagues at hospitals. I won't mention them all by name, but I just want to make sure that you recognize this is a long-standing project that has many people involved, and I'm just the lucky one who gets to present it. Okay, so I'm a machine learning researcher, and it's amazing how many people in my community believe that if you train a deep enough neural net on a large enough amount of data, and if the accuracy looks really good on the test set, you're just sort of safe to go and deploy that model and start using it on humans. And the truth is sometimes that's actually correct, and I have done this, I do deep learning. But sometimes this is dangerously wrong. And just to borrow a quote from Rob Califf, who just spoke, you know, people like me whose lives are tied up in this sort of work that we're doing and really believe in it, sometimes have a hard time recognizing the sort of harm that we can do if we're not as cautious as we should be. So thank you for the quote, Rob. Let me tell you how I got into this. So back when I was a grad student at CMU, there was a big study going on, CMU, UPMC, training machine learning models for pneumonia risk. And I got asked to train a neural net. We were doing this retrospective study to build a decision aid for pneumonia. And the goal was to try to distinguish between low risk and high risk pneumonia patients. You know, low risk, treat you as an outpatient, chicken soup antibiotics, call us in a few days if you're not feeling better. But if you're high risk, you definitely need to be in the hospital. I mean, it's a serious condition if you're a high risk patient. And our goal was to look at the various machine learning methods that were available back then, this is before deep learning happened, and see which of these would be best at distinguishing between high-risk and low-risk patients. And I got lucky. Of all the different teams who were working on this project, the stuff that I was developing at the time, multitask neural nets, turned out to be the best model that we could train on the data. And then the question was, you know, is it safe now for us to go ahead and consider using this on real patients? And I sort of said, no, we should not use this on real patients. And instead, we decided, you know, what else would we use? Of course, we would use logistic regression, the method that's been used in healthcare for many decades. And we would use that because it's a model we could understand, even though it wasn't anywhere near as accurate as the neural net that we had trained. So why was I so concerned? A friend who was doing rule-based learning at another university on exactly the same data set said, Rich, I learned this funny rule. The rule is that if you have a history of asthma, it lowers your chance of dying from pneumonia. That is, asthma seems to be protective for pneumonia. You know, what do you think that means? Because that didn't make sense to us. So we went to the next big project meeting. Real MDs were involved in this project. And the MD said, well, first of all, we consider asthma to be a serious risk factor for pneumonia, so we don't want your model to predict that asthmatics are lower risk. But we can kind of see why a model trained in this data might learn that. The asthmatics are paying a lot more attention to their breathing. They might have an inhaler or other meds that don't seem to work if they suddenly have pneumonia but don't recognize it. They probably have a doctor who they can get in touch with. And then once they're diagnosed with pneumonia, they get particularly high quality care. They might even be admitted to the hospital or the ICU because the doctor takes it seriously. So the miracle for the asthmatics is that they sort of notice the problem earlier, they get to healthcare earlier, they get to diagnosis earlier, and then they get to aggressive treatment earlier. And those things are so effective that it turns out the asthmatics actually do have half the probability of death compared to the general population who doesn't get to care so quickly. So now, I just assume if a rule-based system learned this rule, that somewhere hidden in the 10 million weights of my neural net is the same pattern. I just don't know where it is. Okay, so I don't know exactly how to find this thing. I just assume it must be there because the two models were trained on the same data, and in fact the neural net is more sensitive than the rule-based system, so it's probably there. Now you might think that the asthma problem is why I was afraid to deploy the neural net, and it's not. I actually said, look, I'm a smart guy. Now that I know about the asthma problem, I can probably figure out how to make it go away in the neural net. I can find it and get rid of it somehow. I said, what really scares me is that we only know about the asthma problem because somebody trained another model, like a rule-based system that we can understand, and it's the thing that told us about the asthma problem and then told me I need to fix the neural net. And I said, what else did the neural net learn that the rule-based system didn't learn because it's not as sensitive, which could be just as risky as this asthma problem if we were to deploy the model, but I don't know that I need to go fix it. So that was the real concern, was these unknown unknowns that might be lurking in the neural net that would be risky, just like this asthma factor, which we now sort of understand. So now, this is a much more fundamental problem than you might think. You might think, oh, this is just this particular data set. It's not. Most data does not come from RCTs. You know, when we're trying to do machine learning, it wouldn't even be ethical to collect the right data for asthmatics. Like, we can't kill a few asthmatics to train a more accurate machine learning model. We can't send half of the asthmatics home or not give them the right treatment or give them rapid treatment. So the fundamental problem is that there's a confounding that's occurring because we're missing some important variables. And the two important variables we're missing here are time to care, how rapidly the patient got to diagnosis and care, and then the quality of the care, the aggressiveness of the treatment. Those are the two things we're missing. And if you think about it, you know, every data set you have has some features missing that you can't have. So for example, time to care is something that would be very hard for us to measure for pneumonia because we don't know when you came down with pneumonia in the first place. So it would be a difficult thing to have, even though we now recognize it would be a very important thing to have. Also, there are other variables, other medical tests that we might know to do in 20 or 30 years. They're not in your data set now because we don't even know about them yet. And they are creating exactly these same sorts of confounding problems with the variables that are in your data set. So even things that we don't know about yet, even if we could collect them in 20 or 50 years, even those things are causing these sorts of issues in your data set. And as I'll show you in a few minutes, there are even more problems in the data set than these. Now, you might think the challenge is just to understand the data. You would have recognized this problem in advance, and then you could have somehow cleaned the data. Well, that's actually quite difficult. One, I don't know how to collect the right data for asthmatics, because as I said, it's not even ethical to do some of the things that we would need to do. But also, it's very hard in advance to sort of anticipate these kinds of problems. They're the kind of problems that once you see them, you sort of hit yourself in the head. It's like, oh, of course. That makes perfect sense that it did that. I should have anticipated that. But it turns out you didn't anticipate it, and there's a lot of them there that you would have to anticipate. So it turns out it's much too hard to just sort of say, oh, it's the responsibility of having clean, correct data. That's actually much too high of a bar. So our bar is going to be to just try to understand the model and be able to recognize things in it. By the way, although I won't talk about this anymore today, it's exactly the same story, this asthma problem with pneumonia. It's exactly the same story if we're worried about things like race bias, gender bias, socioeconomic bias. It turns out all of this is bias that's being learned because of confounding effects. And that's just sort of ubiquitous in many different ways, not just in healthcare. So all we would need to really solve this problem would be to have some sort of model that was as intelligible as logistic regression, but which was going to be as accurate as that neural net. Now, as many of you might know, there's this trade-off, unfortunately, in a lot of machine learning where the models that are most intelligible, things in the bottom right, like logistic regression and naive Bayes, they're very intelligible because of their simplicity, but unfortunately, they tend to be less accurate on complex data sets. And then the things in the upper left-hand corner, the things that are modern high flyers like deep neural nets and random forests and boosted trees, unfortunately, these things are pretty complicated, and you tend not to be able to understand what they've learned. So what we really want is something that's in this upper right-hand corner, which has high accuracy and high intelligibility. And to our surprise, we've had a little bit of success putting at least one algorithm in that corner, this thing called generalized additive models with pairwise interactions that we've been working on now the last 7 years at Microsoft. So I'm going to tell you a little bit about those things. I'm not going to tell you about the technical details of how the algorithm works. Instead, I'm going to show you the kind of thing we can learn from those algorithms when we apply them to a healthcare data set. So You've got this space of models. At the top, you just have linear models. Don't worry, this is the most math we're going to have in the talk. You have the space of linear models, weight times a feature, weight times a feature. And at the bottom, you've got full complexity things. It's just some arbitrarily complex function of all the available features. Fortunately, there's a space in between. And this is the space of additive models, which many of you have probably heard of. These are a function of a single feature plus a function of another feature plus a function of another feature. The functions can be complicated, but they can only be functions of one feature at a time. That's a tremendous restriction on the complexity of the model, and it makes them very modular and interpretable, as I'll show you. And what we're going to do is we're going to restrict ourselves to functions of individual features and maybe a small number of functions of pairs of features, although today I won't show you any examples of pairs of features. Now, we're at Stanford. This is not something I put into the slides just for today. I always say this. We didn't invent these generalized additive models. They were invented here, and they were invented here in the late 80s. So these things have been around. They predate a lot of machine learning. These have been around a long time. And our contribution is going to be to sort of put machine learning steroids on them. We're going to be less conservative than statisticians were when they fit these models. And in the process of being less conservative, we're going to get both a lot more accuracy out of them, and surprisingly, that accuracy is also going to bring more intelligibility. So that's what we're going to do. OK, I'm going to skip all the details. I got permission, once we got these working, to go back to this pneumonia data set that was collected in the early 90s and that I first worked on in the mid-90s. This is some of the features that are in that data set, things like respiration rate, body temperature, blood pressure. A doctor has seen all these patients, taken some notes about their breathing. There's been a chest x-ray for all these patients. A doctor has also read the x-ray, taken notes about that. We have some blood tests. These are about half of the features. You might be able to tell that's dot matrix print, actually, so that gives you an idea how old this data is. Back then, this was considered a really massive medical data set for machine learning. Now, it would be considered quite small, 15,000 patients, and only 46 features. OK, now every one of these features that we have in the data set is going to have a function grown around it. So you can think of it as being this way. So age is one of the features. There's going to be a function of age. There's going to be a function of blood glucose. There's going to be a function of blood pH, a function of your creatinine level. And each of these things, the model is going to learn a function of all these things all in parallel. And the way you use it is you look up the patient's age, read off the Y value and write down a number like minus 0.23. Look up whether they have asthma or not, which is a Boolean, and that's a minus 0.15 for a patient who does have asthma, asthma being protective for the patients. So you write down all these numbers, and then it turns out it's very easy math. You add up all the numbers. The more negative the score, the lower the risk. The more positive the score, the higher the risk. It's just log odds. At this point, it is just logistic regression. It's something you're very comfortable with. So the only thing that's new here is the fitting of these functions. So let me show you. This is a graph. I'm going to step down here so I can use a mouse and walk you through this. This is a graph of what the model has learned about age. So this is no cursor. Don't worry about it. The bottom is a histogram of the ages of the patients that we see in the hospital. You can see most patients are between, say, 60 and 90, some patients in their 20s through 50s, and a few patients over 100. And then the graph above it is what the model has learned about risk of dying from pneumonia, so probability of death, as a function of age. So let me walk through that graph. So let's see. Below 50, it's pretty much a flat line. It's sort of minus 0.3 almost. So it's good to be young. So the model seems to think that everybody under 50 is young. The model could distinguish between people who are in their 20s or 30s or 40s, but it doesn't. It just sort of puts them all into one category. They're all under 50. They're all in the lowest risk group. Then risk seems to go up slowly as you go through your 50s and 60s. That's good for me. And then risk rises a bit as you get to 67, 68. And then it continues to go up pretty quickly as you go through your upper 60s, through your 70s, and into your 80s. And then there's a surprising step function of risk happening at 85, 86. And then risk is kind of flat. That's also surprising, say in your upper 80s and in your 90s. And then there's an even more surprising drop in risk that's happening around 100, 101. So let's talk about a few of these things. The rise in risk that's happening at 67, 68, we're almost certain that this is due to retirement. So this would have been a very common retirement age back then. When we work on modern data, we see it shift to the right because retirement gets later. This is pretty certainly a retirement effect. It's unfortunate that retirement is bad for you as opposed to good for you, but but there are many things that happen at retirement. You can understand how that could be. I mean, your provider might have changed, your daily activity might have changed, your insurance may have changed. I mean, you may have moved, not even have a doctor yet, all those sorts of things. Then risk goes up pretty rapidly, and then you get to this weird rise at 85, 86. Now, you guys can tell me. My understanding is there is nothing in insurance code or in healthcare policy that says we should treat somebody who's 86 differently than somebody who's 84. If anybody thinks that's wrong, raise your hand, because, okay, good. And in data sets back then, my understanding is some of the healthcare data sets, they didn't even bother to record if you were over 85. They just checked 85 and over, right? Because over 85 was like the old side of old back in the early 90s, right? 95 is the new 85, but back then this was really being on the senior side. And we think it represents a decision to not sort of continue to give aggressive care for patients who are over this round number of 85 years old. As in, grandpa's already had 2 rounds of antibiotics, has a number of comorbid conditions, grandpa's very sick, will probably pass away in the next 3 years, perhaps. Maybe we should just let grandpa pass. And as some of you may know, pneumonia was once called the old man's friend, right? Because it would sometimes save you from a sort of long, withering, lasting illness. You'd suddenly get pneumonia at some point when you were sick enough, and then 3 to 5 days later, you had passed away. So we think that this rise that the algorithm's detecting is just a social effect, just a collective decision by doctors, by the patient, by their children, to not continue to treat as aggressively for patients who are over this bar. The flatness at 85 through their 90s, David Heckerman, who I think is in here somewhere in the room, there's David. David suggested this might be a sign of what's called successful agers, people who have very good genetic mix, who haven't damaged themselves through their lives, and at least from the point of view of a pneumonia condition, might not really be at that much elevated risk if they're 95 compared to, say, 85. And then there's this weird drop that's happening at 100, 101, and we think, again, that's happening at a round number. So when you see round numbers, you should always suspect some human intervention in the process. We think this is the opposite of what's happening at 85, as in, you've made it to 100. You're a centenarian now, which was pretty remarkable back in 1990. We think it's a decision, we're just going to go for the record. We're going to, we're not going to give up now. We're just going to keep fighting. And you can see a sign that that's probably effective. Now, I could talk about the error bars. It turns out we've done more statistical analysis, and it seems to be a real effect as opposed to just noise in the data. Okay, so now, who thinks we should deploy a model that thinks people who are 105 are less risk than people who are 95? That people who are 105 actually need less care? Like that doesn't make sense. So we'd probably want to edit the model so that risk goes up maybe slowly, monotonically, as you go through your 90s and past 100. So we would want to edit this model. This rise in risk at 85, I'm actually happy to leave that in the model, because if the model predicts higher risk for patients, then maybe they'll actually get better quality care, and maybe that'll help mitigate us making decisions to give them less quality care. So, and it's safe to predict that people who are very high risk are already a little higher risk. So I'm actually happy to leave that in the model, but I probably would want to tell doctors and patients that maybe they should think twice about deciding to withhold treatment and should fight harder, because we're seeing a sign that by not giving aggressive treatment, that patients actually are dying earlier because of it. And then this retirement thing, I think we'd just love to, if we get to collect the data again, add a retirement variable to the data set. That'd be great. It would probably make this graph be smoother in that region, because now this retirement effect would be captured presumably more accurately on another retirement graph. Okay, so that would be great. Some comments about this model. So this model is 46 graphs plus 10 pairwise interactions. So it's 56 graphs. This is not an approximation of some more complex animal. This actually is the model. You can use this model by printing it on 56 pieces of paper. And if you can read the paper to 2 decimal places, you can actually find the patient's age, write down the number, go to their asthma, write down the number, go to their blood pressure, write down the number, add up all those numbers. And that is exactly what the model is. Now, it turns out 100 million trees died in the process of creating this model. By trees, I mean decision trees, sorry, not the rainforest. Many decision trees died to create this model, but once we have the graph, this is the model, and we throw the trees away. So this really is what the model is. Another interesting thing, this model, it turns out, is actually a little more accurate than the neural net. It's a little more accurate than anything else we've been able to train on this data. So by using this model, you're not having to pick a sort of lower accuracy to get something this intelligible. This model on this data set is just as accurate as anything else. So there's no loss there. And yet this model's extremely intelligible. I mean, there's 56 graphs. I wish we had time to go through a bunch of them because especially as clinicians, you would understand a lot of fun stuff that's on these graphs better than I would. But all these interesting details that we're seeing and corrections we want to make to the model, these are all things, because the model is so interpretable and transparent, we can see exactly how the model thinks and makes its predictions. Okay, and then we can even fix some of those things when we think that they're wrong. Okay, and I'll show you a few more things that are wrong in this model. Let me talk a little bit more, though, about whether this model is right or wrong. Suppose the model needs to be corrected if we're going to intervene in people's health care, right? Because we don't think we should predict lower risk for people who are 105 than people who are 95, right? None of us believe that's an intrinsic truth about risk in patients. Suppose, however, we're an insurance company, and our interest in making a prediction of survival is purely actuarial. Okay, we want to know how much money to have in the bank, what to charge our patients, our customers, things like that. Well, then we're not going to intervene, presumably, in their health care. Now it's actually perfectly fine to leave the model the way it was. That is, it is true that, in fact, people seem to have lower risk once they break 101. As an actuarial organization, I might be very interested in knowing about that. And that's not something I feel I need to fix because I'm not going to use the model in a way that would put patients at higher risk. In fact, it's telling me more accurately about what I need to do with money in the bank. So that's important. It means that model correctness, accuracy, is not some fundamental property of the data or the model. It's a property of the model and how you're going to use it in the real world. The model can be perfectly appropriate and the data perfectly usable and correct for one purpose, and yet for a different purpose, that same model has some dangerous things in it that you really need to fix before you would ever consider applying it to real patients. Okay, so that's very, very important. And notice, it turns out accuracy is just not a sufficient measure of model goodness or utility in the real world. And that's because almost always we measure accuracy on test data, and our test data tends to look like our training data. So this model, when I correct that problem with asthmatics or I correct the problem above 100, it turns out its accuracy on test data goes down when I correct it. But I believe its utility or correctness in the real world will go up by correcting it. So that just sort of further tells you that the accuracy on test data is not a sufficient way of measuring whether these models are actually safe to use or correct to use. Let me just show you a few things the model learned. It's interesting. Okay. First of all, there are lots of jumps that happen at round numbers, things that happen at age 21. So there's fun stuff that happens at creatinine. When it goes up to 5, it rises, and then it drops, and goes up to 10, and then it drops. It goes up towards, I assume these are treatment effects where we start to intervene in the patient's care when we hit these magic thresholds. There are lots of things that are jumps. And a lot of these jumps, like your body doesn't know the units that we use to measure these things. So what are the odds, that a jump in your body's response to something is going to happen at a round number? But people know these units, and people think in round numbers. So a lot of the jumps in the model that happen at round numbers are always due to humans somehow intervening in the process. So that's interesting. The model, first thing I did was I checked to make sure it learned that asthma lowered risk, and it did. Remember, that's a real pattern in the data. I expected that, so I was very happy that it learned that. The beauty, though, is that this model is as accurate, more accurate than the neural net, but I can now see the asthma problem in it, and I can fix it. And I'll talk about fixing it in a second. Here's the interesting thing. The model, unlike the rule-based system, also learned that chest pain and a history of heart disease are good for you. In fact, it turns out that heart disease is better for you than asthma. And it's exactly the same explanation, right? If you've had a heart attack, you wake up today and you're having a little trouble breathing, your chest feels a little funny. I mean, within an hour, you're in an ambulance or you're at the ER. And if you go to the ER, you get to the front of the line and you get probes attached to you very quickly, right? I mean, there's a concern that you're having another heart attack. And what's the best thing that can happen to you if you've got pneumonia is that you get incredibly rapid diagnosis and then you get very high quality treatment. And they basically have good news for you. You're not having a heart attack. You just have pneumonia, if the diagnosis is correct, and then you get very aggressive treatment. So in fact, the heart disease patients do even have lower chance of death than the asthma patients, but both of them should have higher risk of death if you were to properly treat for time to care and aggressiveness of treatment. Okay, so it's good we didn't, we were concerned about deploying that model because of these unknown unknowns back in the mid-90s. It's good we didn't deploy it because while I would have fixed the asthma problem, I wouldn't have known about the 100+1-year-old problem or the heart disease chest pain problem. And it turns out there are other problems in the model as well. I wouldn't have known about these things, so I wouldn't have known to fix them. But these models are so interpretable that we can now see these things and fix them. Here's the strange thing. The way to fix them is you take these variables you're afraid of and that you have learned bad things about, like race, gender, black, white, male, female, heart disease, asthmatic. You have to keep those variables in the model. You let it learn the bias that's in the data set. You let it become as biased as it possibly can be. And then afterwards, you can see it, and now you can also fix it. You can do things like delete those terms, put zero weights in front of them. And then you have to not retrain the model. And once you know about these problems, you have to make sure that in the future, you always include those variables in the future as well. Because the problem will not go away if you delete the features, and that's because there's correlation between your heart disease and other variables that are going to be in the model. The bias is in the labels, it's in the outcome, it's the fact that patients survived or not. So you're not going to make the bias go away. And because of correlation with these variables that you are afraid of, like heart disease, and other variables that are in the data set, it turns out the model will still, through correlation, learn to predict that heart disease patients are lower risk. But now it'll be spread through the model in a way that you can't detect. And unfortunately, it'll be much harder to fix it, even if you knew that the problem was still there. So this is a surprise that you actually have to keep the things you're most afraid of in the model. Let it learn the bad things, and then afterwards you can remove it. I don't want to give you all gloom and doom. First of all, we have now a model class that for some problems is just as accurate as anything else, and it's extremely intelligible and in fact editable. But we can also learn some good things from the model if it's interpretable. So this is risk as a function of blood urea nitrogen. And it turns out that what doctors said was interesting about this was they thought of 50, again a round number, as being the threshold at which they would start to intervene if they saw a blend above 50. And they said what's fun about this graph, what's interesting is it says at 40, the risk is already quite high. And maybe they should reconsider whether 50 is the right threshold, and maybe 40 would be a good threshold. Okay, let me just wrap up. AI systems make very different errors than humans. So they didn't go to med school. They don't know what a human is. They don't know what death is. They don't know that asthma and pneumonia are both things that affect your lungs. And that probably asthma is not good for you, all of the things being equal. So they make very different kinds of error. And that's because they're trained on a very limited data set, as opposed to all of us who are trained on a much broader data set through our life. So they just don't have the context in which to understand these things. And high accuracy on a test set, if somebody says, oh, it's got superhuman accuracy, and that's on just test data, don't believe it yet. It's only once the model is deployed, operating in the real world, and you have a good way of measuring its accuracy in the real world, that you could actually say something like it's exhibiting superhuman accuracy. This class of models gives us this nice combination of high accuracy and intelligibility and transparency, and that's really wonderful. It helps us find problems that we wouldn't have expected. Most of what we see in the models is actually beautiful. It's great. We're very impressed. But every now and then we see some things that are risky that we really have to fix before we deploy the models. And then the surprise is it's very important to keep these offending variables in the model so that the risk is localized to those variables and that you can see it and then have a way of sort of surgically removing it. Okay, I should stop.
Thanks so much, Rich. Really great kind of insight and technical expertise to kind of share with us. Really kind of one of the key themes, essentially explainability, interpretability, And some think that's why a lot of AI or decision support ideas for 30, 40 years won't work. Because doctors say, if I don't understand what you did, I don't trust you. And yet, can anyone explain to me how propofol works? Can anyone explain to me how Tylenol works? I still use those all the time, though. What's the difference?
Right. So for drugs, at least we have a long procedure, a series of bars that you have to get over before the drug gets into general wide clinical use, right? And not only that, so not only do you have to, my understanding is these days you even have to have a proposed mechanism of how the drug would work. You have to have done animal studies, then a small number of human studies, and larger clinical trials on humans. And even then it's a cautious rollout. Not only that, but there's a tracking system in place to help try to recognize adverse outcomes, complications that happen after the drug is released. And as long as we do machine learning systems with, say, all those same kinds of safeguards, then I guess it would be fine. And you wouldn't have to understand how that deep net works if you make it go through that similar set of hoops and you're carefully monitoring it once it's in the real world. That would be fine. I think this intelligibility is just one of the tools for helping us as quickly as possible get rid of some of the risky things that a model might do before we start applying it to humans. So what's frightening is that the models tend to make their biggest mistakes on the things that we're most capable of detecting and treating. Like, they're most likely to think that heart disease patients are low risk, and that's because we actually have effective treatment diagnosis for these patients. So it's kind of sad that some of these machine learning models might make their biggest mistakes on the cases that humans, the current medical system, would be most likely to get correct. But if we trust these models too much, it might actually make catastrophic.
One quick question from Linda Pormacina. How do you determine if you have enough data for people over 100 years old? I'm pretty sure there's not so many of them. How can you know anything about them?
It's a good question. So one of the beauty of statistical methods, as opposed to, say, modern machine learning methods, is that there are much more reliable ways of computing confidence intervals in statistical methods, because statisticians have been taking confidence intervals seriously for decades, right, for a long, long time. And it's still kind of a new word to a lot of people in machine learning. So I've been working with statisticians who have helped us come up with some new confidence intervals that are appropriate for this class of models. And the beauty is that those confidence intervals are even tighter than what I showed. And they basically suggest it really looks like it's real, a real effect. And we've also seen it in multiple data sets now. So that also increases our confidence. We see the centenarian effect in multiple data sets, where we just push harder if you've made that number. Yeah.
Excellent. Thanks so much again, Rich Caruana. Thank you so much.
The preceding program is copyrighted by the Board of Trustees of the Leland Stanford Junior University. Please visit us at med.stanford.edu.